Hi. I'm Jim Heffron. These are my lessons in calculus. So we're doing right now the homeworks for the section on the derivative of trigonometric functions. And we are kind of working our way through derivatives. We're gradually becoming more and more capable, able to take the derivative of a product of two functions of x, for example, doing trigonometric functions now. We're working our way up, being able to do more and more and more. Okay, let's get to it. We're going to do the homeworks, and as always, when we do the homeworks, we're going to spend time doing a material from a prior section, recalling to our mind the material from prior section, because the way that you make it permanent in your mind is by keep on recalling it. Okay, let's see here. So the problem from the prior section that happened to land on is section 2.8, number 3. I don't know, sometimes I pick earlier ones, sometimes I pick later ones. And again, these what I'm showing now is the Stewart book, the Stewart calculus book, just to give credit where credit is due here, and problem number 3. And so it says match the graph of each function with the graph of its derivative. And so I'm simply taking A and figuring out which are the red ones, the graph of its derivative, taking B, etc. Okay. All right, so let's see. For A, I see that it's going down pretty sharply, and then it's 0, and then it's going up maybe at a rate of 1, and then it's 0, and then going down pretty sharply. So I'm looking for a red graph that is pretty well negative, and then 0, and then positive 1, and then 0, and then pretty well negative. So I'm looking for a graph that is pretty well negative, and then 0, and then positive 1, and I think I'm looking at this. Pretty well negative, and then it's 0, and then it's positive 1, and then it's 0 again, and then back to pretty well negative. So I'm thinking the derivative of A is Roman 2. All right? So let's say B. I'm looking for, not a curve here. Well, it's a curve, but it's a straight line. Maybe 1, maybe minus 1, maybe 1. I mean, I'm just eyeballing it, but it looks sort of 1-ish. So I'm thinking that's 4. Maybe 1, maybe minus 1, maybe 1. I note that there's an open circle there and an open circle there, and that corresponds to the fact that there is no derivative here. Open circle here corresponds to the fact that there is no derivative here. So I think B matches with Roman 4. So now on to C. I'm looking here at, when I look at the rates of change of function C, I'm looking here at a rate of change that is slightly negative, and then 0, and then slightly positive. Okay. So I'm thinking that's Roman I said the words slightly negative, and then 0, and then slightly positive. Seems to me to fit. Right? Slightly negative slope, then a 0 slope, then a slightly positive slope. Okay, and the last one, getting good at this. So I'm talking about the slope of the blue curve here. So I think I'm looking at pretty positive, and then 0, and then a little bit negative, 0 again, a little bit positive, 0 again, and then pretty negative. So we've done 3 of the 4, so let's see how we do. So pretty positive, and then 0, and then a little bit negative, and then 0 again, and then a little bit positive, and then 0 again, and then pretty negative. So I think that fits. So the slopes of the blue curve are the red Roman 3, I think. So I think that fits. Okay, great. Okay, so what that question, of course, has asked me to do is to think about the derivative as a rate of change, not as some kind of algebraic manipulation of formulas, but as what it means, as a rate of change. So it's good to go back and rethink about what it is that you're doing. Next up is section 3.3, and I decided to do example. What happened to me here? I decided to do example 3, but it somehow didn't end up on the slide. So anyway, I'm going to do it. So example 3, if I can find the darn thing, there it is. Example 3. Come on. Example 3, if I don't knock over everything on my desk. It says an object is fashioned to the end of a vertical string, like so here, at spring and is stretched 4 centimeters beyond its rest position. So you take this weight and you let go, and it starts to go up and down and up and down and up and down. Its position at time t is given by this formula. S is 4 cosine t. Find the velocity and acceleration. All right, so it says use them to analyze the motion of the object, but I'm just simply going to find the velocity and acceleration. So here's the picture. I didn't realize I didn't have the picture on the screen. So you pull that weight down and let go. And then it starts going up, down, up, down, up, down, up, down. And its graph, it's a graph of the function. Its motion will give you a graph of the function 4 cosine t. Okay, so let's have a whack. So f of t is 4 cosine t. Find the velocity and acceleration. So position is f of t is 4 cosine t. And we want to know velocity and acceleration. So velo and acceleration. So the velocity, of course, is the derivative. So the derivative with respect to t of f of t is the derivative of 4. You bring that out, and derivative of cosine is minus the sine. Probably you would write this as minus 4 sine t. Okay, so reminding a person that one of the ways we understand the rate of change that we're thinking about is that you take the function to be the position, and then we're finding the velocity and the acceleration first and second derivatives. So the second derivative with respect to time of f of t is, so the derivative of minus 4 sine t, you bring the minus 4 out and you take the derivative of sine t, which is cosine t. Okay, and you can see that acceleration came out to be the negative of the position, but in any event, I just simply did the algebra, just simply followed the formulas that we did the formulas for sine and cosine today, just simply follow the derivatives formulas that we've done. Okay, great. So that was example 3 that I apparently forgot to type into the slide. And next up is question number 7. So we have a couple of derivatives here. Oh, I'm going to knock that thing over. I don't watch out. So question number 7. Take the derivative of secant theta times tan theta. Question number 11 says take the derivative of cosine squared of t. And then there's also a question number 27 that's not on this page. So just a couple of drills. Just a couple of do this, do that. So let's see. Question 7 says the derivative of secant theta tan theta. That's a product of two functions of x, so I'm going to apply the product rule. Starting to recognize the parts here. So the product rule is you write down the first, secant theta, times a derivative with respect to theta of tan theta, and then tan theta times the derivative with respect to theta of secant theta. Okay, and it's just a question of putting in the parts and hoping that, I don't lose a minus sign. So secant theta, derivative of tan theta is secant squared theta. And then tan theta. And the derivative of secant theta is secant tan. Okay. I'll gather terms. I don't think anything exciting is happening here. Secant cubed theta plus tan squared theta times secant theta. Now there are formulas. A tan squared, for example, can be expressed in terms of secant squared, but I'm going to leave it there. I am going to make a comment, though, which is I and many other people in the world will when you say something like the derivative here, the derivative of secant theta is secant tan, then that's just simply, sort of speeding things along. It's a shorthand. But when you're writing it down, you have to write down the theta, you have to write down the theta, you have to write down the theta. So somebody who wrote something like the derivative with respect to theta of secant is secant tan, I'm sorry, that's mistaken. Okay, so it's one thing to say it out loud, sort of talking to yourself. It's quite another thing to write it down. Okay, great. Let's see, that's number 7, and we're also looking at number 11. Number 11 is h of t. Move my page here. Number 11 is h of t is cosine squared t. Okay. So what's happening here is that we do not yet know how to take the derivative of the square of a function. We don't know how to take what's called the chain rule. It's just a question of doing one thing at a time, that's all. So, so instead, I have to take the derivative of cosine times cosine. All right, so I'm going to take the derivative by the product rule. So h prime of t is cosine of t times the derivative with respect to t of cosine t plus cosine t times the derivative with respect to t of cosine t. So I've got here cosine t times minus sine t plus cosine t times minus sine t. And so I end up, when I'm all done here, minus 2 cosine t sine t. Okay, so just simply following the rules, doing what we know, what we don't know, etc. And then the very last problem, number 27. I think I'm going to put it on the picture here. Very last problem, number 27, says find the equation of the tangent line, and the graph is a sine of x plus cosine of x at the point 0, 1. So we're looking for the equation of the tangent line at the point 0, 1. So did they give me a function name? They do. Y is equal to sine x plus cosine x. And we're looking at 0, 1. So y prime is derivative of sine is cosine x. Derivative of cosine x is minus the sine. Okay, plug in 0. We get derivative of, a cosine plug in 0 gives you a 1. Sine plug in 0 gives you a 0. I know it's a little annoying, but I'm going to write 1 minus 0 and get 1. And so I just simply write y minus y1, which here is 1, equals slope times x minus x1. And just to have simplified the whole thing, we get y equals x, because it's 1 times x, minus 0 just gives me nothing, and add 1. Okay, from bringing the 1 over. Okay, very good. So so the derivative of the cosine, the sine, the tangent, the secant, and even the cosecant, we can do all those. Okay, I've asked you to memorize 4 out of the 6, but you wouldn't kill you to memorize all 6. So we then drop those into the formulas that we have. For example, the formula product rule, whatever formulas you happen to have. Okay, so starting to get more and more advanced here. We cannot yet do something like take the derivative of the square of a function. That's next section. We cannot yet take the derivative of of some other functions like logarithms, but we're getting there. Okay, great.